Okay, so I'm starting the recording. Welcome everybody to this week's version of Statistics Can Be Fun. Is anyone having fun yet? No. How's everyone going?
I'm enjoying learning all sorts of things, Megan. And
that's great.
Getting my head around all the basics. It's fabulous.
Excellent. Very, very good.
I think it's going to make next year more fun for me, Megan. Even if it's not super fun right now while I'm getting my head around things again.
What are you doing next year, Elise?
I'm doing my honours. Well, as you know, I'm doing my honours, but I'm doing part-time. So this year I've only done 3 units and I've got 3 next year to go. Statistics being one of them.
Cool.
Yeah.
And are you doing your thesis next year?
Yes.
At the same time. Okay, awesome.
Yes. Yeah.
Good job. All right, so we might get started. Now, just a little bit of a recap on what we looked at last week. So last week we were looking at descriptive statistics. We were looking at running continuous descriptives and categorical descriptives as well. And then we had a look at some correlations. So a correlation is just the relationship between 2 variables. And those variables that were correlated or had a relationship with our dependent variable were the ones that we would then decide to put into our final statistical model. So that's kind of where we're up to today. So the first step that we took was cleaning the data. The second step we took was running descriptive statistics, kind of looking at what our population of survey participants looks like. Then we looked at relationships between the independent variable, which is the variable that we are manipulating, the dependent variable, which is the variable that we are trying to find out what the outcome is, and the other variables or confounding variables, which are all the other things that could be influencing our model or our dependent variable that isn't the variable that we are interested in, because it's very important to also look at things outside of what we think may happen. So that's where we're kind of up to. So who can tell me from last week, what is our dependent variable of the data set that we were looking at? And I will bring up the data as we do that. Can we see the data set?
Mm-hmm. Yes.
Yeah, great. Okay, so what was our dependent variable? What was the outcome measure that we were trying to find out what the outcome was, basically? Can anyone remember?
Depression rates.
Very good. Oh. Depression, but we were looking at depressive symptoms, not at depression itself, because the scale that we're using or the survey that we used was measuring the symptoms of depression and not clinical diagnosis. So that was a really important part of this and of this data set. But also when you are doing your own research, making sure that your scale is measuring what it needs to measure. Because if we write our paper up and say diet affects depression, we are not actually being very accurate in our reporting. In this case, the CESC measures depressive symptoms across the population or symptoms of depression. Cool. Who can tell me what the independent variable is or what the variable is that we are manipulating?
Their diet.
Mm-hmm. Very good. Diet, and in particular, diet split into 3 groups. Vegans, vegetarians, and omnivores.
Yeah.
Yep. Can you name some of our covariates or our confounding variables? Some variables that could be affecting depression that isn't diet, that are important for us to measure.
All those things.
Gender could be one, yeah.
Age, status, education.
Sleep quality.
Yeah, sleep quality and exercise.
Yep. So last week when we did our correlation matrix, we explored which ones of these were related to or correlated with depression. Does anyone remember which ones were statistically correlated or had a relationship with depression? It's okay.
Can't remember.
It was everything except for the plant-based index. Now, the independent variable has been measured in two ways. First, the DST, which is our dietary screening tool. It is a pre-validated scale. Now, what that means is that someone else out there in the world has constructed this survey of questions on diet, and it has been validated using factor analysis or some other type of statistical analysis to ensure that the questions in the survey reflect reflect diet quality, basically, healthy or unhealthy diet quality. Okay, Dennis, that's cool. No problem. So the problem that we found when we were doing our survey at the very beginning was that in the dietary screening tool, there's about 4 or 5 questions that focus on meat, dairy, eggs, milk, things that vegans and vegetarians wouldn't consume. So the dietary screening tool itself disadvantages people who are vegan or vegetarian because they would always get a 0 on a question that would ask about meat, dairy, eggs, etc. So what we decided to do was we decided to create a different variable called the plant-based index. Now, that's a variable we created out of the dietary screening tool. So it probably needs to be revalidated to make sure that it's still a valid scale. So all we did is we took all the meat, dairy, eggs, and milk questions and we reversed them so that vegans, vegetarians, and omnivores all got a 5 instead of a 0 for saying that they never ate those things. Now, unfortunately, doing that disadvantages the omnivores because they would get a 0 for saying that they ate 3 to 5 serves of meat, dairy, eggs a week, which is actually considered to be healthy using the Australian Dietary Guidelines. So we have a bit of a problem, but when we ran the survey, we're like, let's just check out what happens with these 2 dietary measures. And when we had a look last week, what happened? Does anyone remember?
I can't remember the exact results, but I remember we were surprised.
Yeah, so what happened was when we ran our descriptive statistics across the whole population, so everybody, not splitting it by diet, but across everybody, all in one big pool, the dietary screening tool came out significant, but the plant-based index did not. That sounds about right. However, when we split the groups by dietary pattern, and we split the vegans, vegetarians, and omnivores up, and we looked at the differences between the groups, the dietary screening tool was insignificant and the plant-based index was significant. Yeah. Now this might be because we have overall in our data set, we have probably twice as many vegans as omnivores and vegetarians put together. So potentially we really should do more data collection, but we have what we have. All of the groups have more than the amount that we need for power, which is good when we do a sample size calculation. So we can still run it and get some valid results. However, we need to keep in mind that our group variances are not similar because we've got lots more vegans. So that's kind of where we're up to. So once we've done all that, descriptors and our correlations, we now have to make a decision about the model that we're going to create. Now, from what I remember, does anyone remember the other surprising thing that we found when we ran our descriptive statistics last week? What was the other variable that wasn't diet that correlated really strongly with depression?
Was it gender?
No.
I can just remember there were lots of women. Something correlated with depression.
Does anyone-
Equality?
No,
Can't remember, sorry.
it was social connectedness,
Ah, yes.
Oh, yeah.
Yeah.
social context. So how we eat rather than what we eat. And it was so strongly correlated. It had like a 0.7 correlation, which was insane. So very, very highly correlated with depression, which is really cool because that's something that I found in my PhD. Outside of this data set, that's something I found in other places as well. So when I'm thinking about creating a model for our questions, I'm going to have those things in the back of my mind. What happened in those correlation matrices, the relationships between depression and those other things as well. Now, before we go and run our regressions, so we're going to do 2 regressions today. The first one we're going to do on the total population, just like we talked about, not splitting the vegans, vegetarians, and the omnivores. First, we're going to look at a regression on the total population using the dietary screening tool. Because remember, it came out significant when we looked at the entire population. Then we're going to split the file by vegans, vegetarians, and omnivores, and we're going to run a regression across the groups and see if there's some differences. But this time we need to use the plant-based dietary index as the independent variable because it is significant across the groups. Yeah? And see how important descriptive statistics are to do first? Because if we had just run our model, we wouldn't have known that we needed to use these in different spots. Now, before we do any form of regression, one thing that we need to talk about is assumptions testing. Now, does anyone here know what assumptions testing is?
Well, I have a tiny bit of knowledge that my understanding is that each type of statistical test involves a certain number of assumptions. The one that I'm stuck on at the moment is that I can't think what it is, but you have to have the same variance.
Yep, homogeneity of variance.
Yes, yeah, but I don't know how to explain it better because I just know my data doesn't have that.
Oh no!
So
See,
yeah, I know
yeah.
I'm really struggling with what to do now, but there are for an ANOVA there are something like 8 assumptions.
Yeah, regression has the most out of all of them, has the most amount of assumptions. Homogeneity of variance just means that the variances between groups need to be similar.
Yeah.
Now, in our data set, the variance between our groups is not similar because we've got like 150 something vegans and we've got like 26 omnivores and 70 something vegetarians. So our homogeneity of variance will also be out if we chose to run ANOVAs, which we're not. We're doing regression. So homogeneity of variance is not one of the assumptions of regression. But what assumptions actually are, they're conditions that we need to meet before we can run an analysis, or conditions that need to be met for our analysis results to be valid. Yeah? Now, the common assumptions for all analyses are linearity, which means that your independent variable and dependent variable are linearly related, so they can fall on a straight line. Pretty much any data set that we use is has linearity, except for Dennis's, I think, was not linear. Wasn't your PhD data non-linear?
Correct.
Yes. That's not very common. That doesn't normally happen. So you have to, it's not the end of the world if you don't meet your assumptions. You just have to perform some form of transformation or bootstrap your data, or there's other steps that need to be taken. But you need to ensure that your assumptions are met before you interpret your results. Yes?
I was going to say normality. Is that enough?
Yes. Normality. Now that's one we looked at last week. How did we look at normality last week?
A normal curve?
A histogram? Do we do a histogram with
Yeah.
a
Very
with
good.
a
Histograms
that
are a
curve?
really good way of seeing normality, because if they're on that nice bell curve, then you've got nice normally distributed data. If it's skewed, you got a bit of a problem. However, normality is not normally a major assumption to worry about. If you have enough participants in your sample, then you can apply the central limit theorem and it doesn't really matter. Normality of your data set doesn't matter. What matters with regression is normality of residuals. Now, you run that inside your regression test, and I'll show you that today. Basically, what residuals are, does anyone know what a residual is? She's a tricky one.
No.
Okay, so a residual is just basically the error in your model. So it's what your model is compared to what it should be. And then there's a section of error. If your residuals are large, that means there's a lot of error in your model. That's not a great thing. If residuals are small, then that means there's a small amount of error in your model. So regression is more worried about normality of your residuals than normality of your actual data. So if your DV is skewed like ours is, massively, depression's massively positively skewed, yeah? Because there's lots more people in the healthy area than there are in the tail end of depression. So, and that's normal for depression studies. So normality of residuals, and I'll show you when we get to that, I'll explain that a little bit further. Anyone know any other assumptions that need to be met before we run our data set?
Is there
Independence of samples, I think is the terminology.
Yep, I just call it independence.
Yeah.
Independence is really easily assumed. You use a study design to assume that. In a survey, independence just means that each person in the survey only did the survey once and they weren't influenced by somebody else in the survey sitting next to them. So if you've got two students doing a survey together on a computer next to each other, and one leans over to the other and says, are you sure you want to put A for that answer? Shouldn't you be putting D? And that student changes it. You no longer have independence in your sample. Mm-hmm.
And within in my field, it's a physical. Often it's a physical independence. So you have two samples of two different what's the word, treatments, and your animal, you have to have all your animals independent so they're not all in the same water or whatever you're doing.
Yes, very good. Yes, so independence is always met by the study design. If you've created your study design properly and you've done all of the proper things when creating your study, then independence should always be met. Now we'll talk about the other assumptions of regression as we go through the regression output, because most of our assumptions of regression are actually built into the regression model, which is great. All you have to make sure at the beginning is that you have a linear relationship, which you can check using a scatter plot of the DV and the IV. We'll do that real quick. It's really quick and easy. Graphs, we'll run a chart builder. We want to have a look at a scatter plot. We just want a simple scatter. Yeah. And we want depression, which is our outcome on the x-axis, I hope. And diet on the y. Okay. Okay. So this is our scatter plot. Could we run a straight line through that? Do you reckon?
Yeah. Yeah.
It's interesting though. Look at that. It doesn't seem to be going in any direction. They sort of seem to be in a straight line. They're not going from the right to from the bottom right to the top left, or from the top left to the bottom right. It doesn't seem to have any direction. What's happening there? That's cool. Or not. That might say something about the fact that we may not have a relationship. Although the correlation was. It seems like if there is a relationship, it's very small, like under 5%. Do we know how to read scatter plots? So if the dots start down here in the right-hand corner and go up to the left-hand corner, that means that you've got like a positive relationship, a perfect positive relationship. If it's going the other way, with the lines going this way, from the top right to the bottom left, that means you've got a negative relationship between your DV and your IV, which is what we should have with depression, because as diet goes up, depression should go down. So it should be kind of leaning this way. Do you reckon that's on a lean that way? Or do you still think it's this way? Let's put the line through it and see. I can't remember how to do that. Here we go. Okay, so it is on a negative incline, just. Can you see that? How the line's slightly negative?
Yeah.
Slightly. But yeah, to me, that's very, whoo, that's on the verge of not being a significant relationship. So, linearity, which is what we're talking about, our assumptions testing, before we looked at our scatter plot, is could we put a straight line through that? Have we put a straight line through that?
Yes.
Or are our dots kind of going like this, which is what Dennis's would look like? So, yeah, so they're not snaking about, are they? They're not in a weird U-shaped pattern or anything. They're on a straight line. You can put a straight line through them. So we've got our assumption of linearity is met there. And running scatter plots before you do any sort of analysis on continuous data is always a good idea because you find interesting things. Cool. So that's kind of all we need. Linearity, normality we looked at last week, but it doesn't really matter too much because we've got enough people in our data set. We're more worried about normality of residuals, and independence has been met, hopefully, if we've done our study design correctly. So what we'll do next is we will run, we might run a little bit of a assumptions testing analysis, keeping in mind that most of what we get out of this, we already did in our descriptive statistics last week. So we'll run through it really quickly. So this is another way that you can look at your descriptive statistics as well as your assumptions testing. So you go analyze, descriptive statistics, and explore. So there's many ways that you can do things in SPSS. This is just another way. So to save time, I have put all of our variables of interest in order so that we don't have to go searching for them this week. So I always put the dependent variable first, which is our depression. Then we'll put our IVs, our plant-based IV and our dietary screening tool. Then social connectedness, which was our next most interesting variable. BMI, age, sunlight exposure, sleep quality, and physical activity, which were all our significant variables from last week, yeah? Then we can get some descriptive statistics. We also want to look at histograms, which is what we looked at last week, and normality plots with tests. There's your Levine's test if you were looking at categorical data, which is what we were talking about, homogeneity of variance. And then finally, we want to exclude cases pairwise. Okay, let's have a look at what that gets us. So this is our assumptions testing this time. So we're kind of looking at some of the assumptions of general data, keeping in mind that most of them we've already met already with our scatter plot and things like that. So once again, much of a repeat of what we found last week. There was 284 participants in our sample. Some of them didn't answer the BMI question or the age question, which is acceptable. Some people don't feel comfortable with disclosing that. Some people didn't talk about their physical activity levels, same sort of thing. Now, these are all of our descriptors that we got last week. So we've got our means, our standard deviations, our minimum and maximum scores, our skew and our kurtosis, which I like looking at the histograms, it's easier to look at something that's a visual than the numbers. So you get all those again. This is why it's okay sometimes not to do just your descriptive. You can just do your assumptions, testing, analysis, and get all of that information already. Normality tests. Okay, so we already know from looking at our histograms last week that most of our variables were skewed, right? There wasn't very many that were normal, were there? Do you remember our histograms? Here's one down here. So remember, depression's positively skewed because you've got more people in the healthy range. Now this is reflected, what we found in our histograms last week is reflected in our normality tests. So Shapiro-Wilkes, I'm going to have trouble saying this one, whatever that is, the KS test we call it. I can't pronounce it. They tell us whether or not we have normality in our data set. They're not really that useful because the histograms already tell us, plus normality doesn't really matter too much if you've got a large sample size anyway. But one thing that you do need to know is that tests of normality, you do not want them to be significant. You want them to be non-significant, because if they're significant, that means that you have a problem with the normality. So what is this table telling us about normality of all of our variables? What are they? Significant or non-significant?
I say they're all significant.
They are. That's bad, because that means we have a significant amount of problems with our normality. So you always want your normality test to be non-significant. But we knew this already. We knew this from our histograms. So it's just giving us like a statistically significant for our normality problems that we have, that we're already aware of. The p-pli and the QQ plots also tell us this. So this is the straight line that we are expected to find our data set to lie on. And then the dots are what we actually found. So if they snake around the line like this, then that means we have a problem with normality, which we know already. Same with our detrended QQ and PP plots. You want the same amount of dots above and below the line. There's a little bit more above, I would say. But the important part of our assumptions testing are these guys, the box plots. Now these tell us whether we have any outliers, any participants who may have incorrect data or data that's been inputted incorrectly, and they're skewing the data. So the reason for our skew might not actually be that our data is skewed. It might be that we've put something in wrong, or a participant has faked their survey. So you see that sometimes where participants will just push 1, 1, 1, 1, 1 all the way through and get sick and tired of the survey, or try to actually ruin your data set for some reason. So box plots are really good at finding these types of people. So what they represent is this black line in the middle. That's our median. So can anyone tell me what a median is?
Middle score.
Very good. Excellent. It's the very middle score. The whiskers on our box plot indicate our confidence interval. So if we remember what our standard deviation from last week, what our scores kind of fall between, that's kind of what our confidence interval is. And outside of our confidence interval, these little dots are people who are outside of kind of the average range of the scores. So we can go back, if we think that, if we see these numbers more than once in box plots, or we think that someone's depression score shouldn't be that high normally, we'd go back and check it. But in this case, our CSD ranges from 0 to 60, which is what the box plot's showing. No one's higher than 60, no one's lower than 0. Those 4 people outside the kind of 50, they have high rates of depressive symptoms, but not unusually high or not outside of what we would expect to be normal. So we would kind of leave them. So you've got to use your own judgment when you're doing your assumptions testing and deciding what to do with your data at this stage. There's our plant-based index histogram. And as expected, there's lots of people who are in the kind of healthy range, but we have someone down here. Can you see this dot here? That's one person with a really low score on diet quality. Can you see that?
Mm-hmm.
And can you see how that person is skewing that whole data set?
Yeah.
If that person wasn't there, all of that would be shuffled over into the middle and would be very normal. Can you see that?
Who is this person?
We're going to have a look. Because when I was doing this before we came on today, I was like, who is that? And I went and checked it out. So we will do the same thing. Now here is the QQ plot. Now it's kind of showing us the same thing. Most of the dots are like on the line. It kicks up at the end there and down at the bottom there. They're just our people on the lower and upper ends of diet quality. But look over here at this person down here near 20. That's the same person as this one here in the histogram. That's super low diet quality. Someone with really low diet quality. So we want to go and check them out and see what the rest of their data says and see if they got tired at the end of the survey and just wrote whatever. Because the diet quality questions were the last thing that we had in our survey, so that we didn't end on a bad note. So we didn't end with the depression questions. Same, the person on the QQ plot down here at number 20, right down the bottom. That's really odd. Now, our box plot tells us there's kind of a few people hovering about in the lower diet quality section, but number 68 is our person. They're our person who we are concerned about with that low diet quality. So let's go and have a look at their data and see whether or not they have completed their survey correctly and whether this is an actual piece of data or not and whether we remove them. Yeah? 68, where are you? Here we go. Okay. Oh, that's on the variable view. Silly me. 68. Okay. That's right. So they're all the totals. We don't need that. Start with age. So participant number 68 is 38 years old. She is a female. She is 165 centimeters and 170 kilos.
Oh dear.
So that's quite high, isn't it? Her BMI is 62. Remember we were talking about the BMIs last week and how that was an unusual BMI, that was an outlier? So this is someone with an extremely, extremely high BMI for height. She's unpartnered. She has a high school education level. She's vegetarian. Let's have a look at anything else in here that might be of interest. Let's go to the dietary screening.
Is this a real person?
Yep. This is all real data. Okay, so here's her dietary screening tool questions. Never, 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 none, none, zero. Never, 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 never. So she is scoring super low on her diet quality. But I don't think that this is a non-genuine answer because of her BMI.
Megan, all the nevers are never what? I can't remember.
Oh, yeah. Okay, let's go back to the variable view.
What does she never do?
Okay, so here are the questions. How often... Oh, that's annoying. Go back. How often do you eat whole grain bread or crackers? Never. Where did that go? Here we go. How often do you eat whole grain cereals? Never. How often do you eat lamb, beef or meat? Never. Obviously, she's vegetarian, so she obviously never eats those. But it'd be interesting to see what her scores are on the PBI as well. How often do you eat fish or seafood? Never. How many different vegetable servings do you usually have at your main meal. I think she said 1.
What does she do?
As in, like, work-wise.
What does she eat?
We didn't ask her that. Well, no, do you know what's not represented?
What?
Or we'll just say, how often do you eat chocolates and sweets? How often do you eat soft drink? How often do you eat pies and sausage rolls? Be interesting to see what she did for those ones.
All the time.
Yeah.
That's what I'm thinking. Takeaway foods, fast foods, and things maybe.
Yep. So her diet would be high in processed foods. So this is another thing that we're finding in the research on vegetarian diets and vegan diets, is that you've got 2 cross sections of people. Those who eat really high, healthy quality, fresh fruits, whole foods, and then you've got your other side that eat all those vegan, vegetarian, processed, fake meat products. Yeah? They're exactly the same as omnivores, who either eat these really healthy, whole food, fresh diets, or super highly processed, refined, sugary diets. Exactly the same thing, just one's plant-based, one's meat-based.
Wow.
Yeah.
That's interesting.
Yeah, it's cool, hey?
What's her social connection?
Yeah. Yeah, what is it? Let's have a look. Social connectedness score is 27, which is...
You should send an ambulance for her.
Well, there's a lot of people like that. Social connectedness score, where is it? Up here. What did we say? 27? Range from 8 to 48. Yeah, that's quite low. All right, let's go and have a look back at our data. So, looking at that, as researchers, we would assume that that was correct data, that she wasn't faking it. She was not just putting nevers because she was tired. That reflects kind of what the rest of her data says. Cool. Let's go have a look at the rest.
Megan.
Yeah.
Do you know what phenomenological writing is?
Is that when you write about someone else's experience from their point of view?
This person, you said that in the vegans and vegetarians, you will find 2 groups. One has a really great diet, and the other goes to the shop and buys packets of vegan and vegetarian food. This person. And so you can write about an exemplar of a particular group. You take one person and you say, this is what this person does.
Yep.
And you just write about who they are and what they do, and they form, it's a really interesting learning experience because they're a complete example of this type of person.
Yeah, yeah.
She's doing everything wrong.
It's interesting. We also asked a question about takeaway food. Let's go have a look at that.
And I'm wondering about exercise.
Well, she can't exercise. She's too big.
That was exactly what I was wondering.
Her physical activity score is 0.
Now,
So-
did you ask about disabilities?
Nope. That was not
That
a
would
question
be an
that we-
interesting one.
Yeah.
No, but that would be interesting. If she can't exercise, she may have some disability apart from being overweight.
Yeah, that's true. Where's the takeaway question? There it is. Takeaway 1. Let's go have a look at what that question was.
Number 18.
Takeaway home delivered meals a week, only 1. So that's interesting in itself. Just wait. Yep. Interesting, isn't it?
It's fascinating.
How long has she been a vegetarian for? More than 10 years. It's a very interesting data point, isn't it?
Now, Dennis and I want to know a lot more about this woman and find out all sorts of things.
She's such an outlier. She exemplifies how you do everything wrong when you think you're doing everything right.
However, when the home cooked question, how many home cooked meals do you eat per week? 1. See, she eats 1 takeout meal and 1 home cooked meal.
So the rest are maybe packaged.
Kilo. She's living on air.
Weird, hey?
Megan, do we have her occupation?
We didn't ask that.
Okay.
But her CESD total score, 0 to 60, is only 21, so she's quite low on depression. even her diet quality, when we changed it over to plant-based, so we weren't disadvantaging the vegans and vegetarians, is still 24. That's still low.
Wow.
Yeah. She only gets a 7 on the normal one because she's a vegetarian, but still on the PBI, she's still quite low. Very, very interesting. Cool. All right. So this is why assumptions testing and descriptive statistics are all very important, because all of these things, getting to know your data set, it takes the longest, to be honest. It takes the biggest part of any data analysis. You'll see when we do regression, it takes like 2 seconds. But doing this pre-analysis stuff is so important, because if that person was malingering or faking, then we would just remove them from the data set and write that up in our report and say, participant 68 seemed to be answering questions in a consistent way, and it did not fit with her other data. However, because it is fitting quite well, we won't remove her. So there she is again on our dietary screening tool, 68, down the bottom there. So she's on the PBI and the DST as the lowest outlier. So removing her would change that that skew again. That'd be a much more normal data set if she wasn't involved. It's interesting, isn't it?
Person enough to change to skew the data all that much?
Yeah, because imagine if you took out this dot here, this data point, then everything would be shuffled over so that the graph would start at 20 instead of at 0. And then the rest of the histogram would be much more normal.
So, but our total N is 284.
Yeah.
And one person is enough to make
Yep, absolutely.
Wow.
Yeah, absolutely. Here's our social connectedness score. Also skewed negatively this time, which is good. That means there's more people up the higher end of social connectedness. The QQ plot's looking a lot more normal. However, we've still got quite a lot of people. It's a little bit snaked. About the same above and below, which is good. And then we don't have any outliers for social connectedness. So that's good. It's a nice normal.
Wow.
Yep, no outliers. BMI, always going to be looking like this. So here's our positive BMI. Most people here in the kind of normal average range, and then we've got quite a few people out here on the snake end who have those high BMIs. And once again, out here right at the edge, there's number 68 again with her high BMI. There she is again, pulling the QQ plots out, making them all snaky, and being weird in the detrended QQ plot as well. There she is at the top of our box plot, all the way up there with her massive BMI. But the BMI box plots always look like this, where they're really squished like the medians down here and lots of people outlying up there at the higher point of BMI. It's normal for our Western population. It's a bit sad, but remember what I said last week about BMI? Does anyone remember?
Yeah, you said it was I can't, sort of like somewhat unrealistic way
Not a very good measurement of,
yeah, that's what, yeah.
It's
Yeah.
a good measurement of height to weight, but it's not a very good measurement of health, because you can have heavier and shorter people who are considered to be obese, but actually just very strong people. Or you can have people who are in the healthy range who are not actually healthy as well.
So those people, you're saying they're muscly, they have high muscle mass.
Yeah, that's right. Or heavy bones,
Okay.
that sort of thing. So it's a terrible measure of health, especially if you've got like a lot of bodybuilders that do your survey.
Even if you've got a really slight frame too. My BMI is just ridiculous, puts me in the unhealthy weight range, but that's just me.
Yeah.
I've always been, so yeah.
Yep. Yeah, and it's not a very good indication of your health, is it?
No.
And they're telling you that you're underweight.
Yep.
Well, I think I must have heavy bones because even when I'm at my thinnest, my BMI says I'm obese.
Oh, see, and
Right.
it's stigmatizing as well.
Yep.
That's the horrible thing, because, and if you think about it, it's not very culturally appropriate either, because it was developed by white people, and people who are from different cultures have heavier frames. Like think about people who are from island countries like Samoa and Fiji and even New Zealand, the Maoris over there. They have, the women especially are bigger than a white Caucasian woman, and their BMIs would be huge when they're actually healthy. So don't get me started on BMI. But still constantly used in scientific research, as you can see here. Age, there's our QQ plot. We got some people who's quite old. That's all right, not a problem.
Megan, I just got a little tangent question. Given that BMI is really not a very good indication of health, would it be feasible for you to not include it and put a little paragraph in your report going, this is basically, BMI is basically a waste of time. So we didn't do it. Or is it so entrenched that you'd get shot down in flames?
Yeah, it's a bit like that. But everybody knows that BMI is not a very good indication of health, but it is a good indication of weight by height.
Yeah.
So I've just seen a problem with our data set. Can anyone see it? Our age range was between 18 and 44. Why do we have people over that age? Didn't we get rid of them last week, Dennis?
I thought we did.
So
we
need to go back and get rid of those people. Yes. Get out of here. They don't fit our inclusion criteria, so we have to get rid of them, yeah? I wonder if participant 68 was in there. No, she was 38 years old, wasn't she? There we go. See, another reason why assumptions testing is very important. We'll do descriptives. It'll catch you when you... We had to get rid of people who were outside of the inclusion criteria. Cool. Physical activity. It's looking weird, but not so bad, because like people do tend to do all different types of or amounts of physical activity. It's very variable, but it doesn't have any outliers, so that's a good thing. And that's our assumptions testing done for now. The rest of it will be in our regression analysis. Any questions about assumptions before we move on? No? Cool. So the next thing that we do is we are going to run a regression on our total population. Now, the reason that we're doing a regression is because our research question and your analysis must always match your research question. Our research question is, does diet affect depression? Yeah, that's simple, isn't it? Does a healthy diet compared to an unhealthy diet affect depressive symptoms? Now, the reason that we run a regression is because a regression will predict the variability in depression that diet takes up. But it will also give us the opportunity to see if we add these other variables that we think also may contribute to depressive symptoms, will diet still play a part in depression? And that's what a regression is for. So let's go. Is everyone ready? It's the fun bit. Regression, we want just a linear regression. Okay, so what was our dependent variable?
Measurement of depression.
Good, excellent. So our measurement of depression, our CESD total, goes into the dependent variable box. Now, when we run regression, we want, remember we were talking about building a model? Now, the most important thing in our model is what? What is our most important variable that we want to test?
That depression.
Yeah, but what are we trying to find out will affect depression?
Oh, the
Diet.
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 Okay.
Diet,
Okay.
probably.
And when we did our correlations, we found out that of the total population, because this is the regression we're doing, the dietary screening tool was the significant one for that. So we will put it into block number 1. Now that's our model number 1. So we want to see, in model 1, we want to see how much variability diet will take up in depression. But then in model 2, remember we found that really interesting thing when we were doing our correlations. So what was it? What was the variable that was so highly correlated with depression apart from diet?
Social interaction.
Social.
Connectivity.
Connectedness.
Yeah.
That's right. So because that's so interesting, we want to put it into the model by itself, just to see what's happening with social connectedness, because that was a really interesting find. So we'll whack it into the second model by itself, because we're interested in what's going to happen there. And then the final model, we just want to adjust for all the other confounding variables. So we want to whack in BMI, age, sunlight exposure, sleep quality, and physical activity all in together, because we just basically want to see what happens when we add all these other variables. Does diet still predict depression? And that's our model. Then we go into statistics, and we want to look at confidence intervals, our covariance matrix, R-squared change, descriptives, correlations, co-linearity diagnostics. Durbin and Watson is one of our assumptions testing. We'll get to that when we go to the output, and diagnostics. So this is our residual outliers. So this is when somebody in the sample has an outlier on 2 or more variables, and it creates a residual outlier. Keeping in mind that all of our assumptions are about the residuals or the error in the model rather than the actual model itself. Then we want to produce a standardized plot of the residuals against the predicted outcome. That's all okay. And then you can bootstrap if you've got some skew. I don't know, I've never bootstrapped before, but potentially this data set could use a bootstrap. That just kind of brings everything in a bit more. Okay, let's run this and see what happens. So here is our regression output. So the first box that we're given is just our descriptive statistics, exactly the same as what we found before. Our means, our standard deviations, and how many people were in our data set. Now, as you can see, it says 273 instead of 284. Why have we lost some people?
Older people.
So I removed 3, so that's still 276. There's still 6 or 8 participants missing.
When we clean the data.
Yeah, so they have to have a response on both the variables. So we've lost a couple of people in there. Okay. This is our correlation matrix, exactly what we looked at last week, with depression running across the top. Keeping in mind that we've looked at these already and we found some interesting things. So just to give you a bit of a recap, as diet increases, depression decreases because it's a negative, but the regression is only 0.186, so that's quite low. That's in the low range. Social connectedness, as social connectedness goes up, depression decreases because of the negative symbol, and it's 0.7, so that's quite a high one. BMI, as BMI goes up, depression increases because it's a positive relationship. As age goes up, depression decreases, which is normal, which is what we normally find. As sunlight exposure goes up per week, depression goes down. As sleep quality goes up, depression goes down, and as physical activity goes up, depression goes down. So this is all kind of in the direction that we are assuming, but some of them are a little bit low quality. Sleep quality and social connectedness seem to be the only ones who have a medium to high relationship with depression at this stage. Now, the next thing that we need to do when we're running regression is we need to make sure that we don't have what's called multicollinearity. Now, multicollinearity is one of our assumptions of regression, and it just means that you don't want any of the variables in your model to be too closely related to each other. Yeah? So to check that, we just make sure that none of the other variables are around 0.8, 0.9 with each other. If they are, that means that they are measuring similar to the same thing. So if we ran the CESD total score and the DAS total score for depression, we would probably find multicollinearity because they should be testing the same thing. Yep, that's why we haven't built them into the model together. So have a look through these regression outputs and tell me if you can see anything that's 0.8 to 0.9.
No.
Sleep quality? Oh no, it's 0.0. No.
0.09, no, that's
Yeah.
okay.
Nothing.
Keeping in mind all these ones here, they're just their relationships with themselves. If you look at the column and the row, so they have a perfect relationship with themselves, which should happen. Cool. So we don't have any multicollinearity. Good, we can move on. That's one of our assumptions ticked off. Great. The next box tells us what we entered into each model: diet into the first model, social connectedness into the second model, age, sleep, sunlight exposure, BMI, physical activity into the third model, just so we remember. Also tells us at the bottom of that box what our dependent variable is in case we forget. And here's our model summary. So this is our first point of call to really know what's happening with this data set. However, always keep in mind when looking at the model summary that it doesn't tell us whether the model is significant or not. Okay, this is just giving us a kind of an idea of what's going on when we add each variable to the model. So model one, with our dietary screening tool, our correlation is 0.186, which it was up the top. R squared, now this is our important one for this one. So R squared in the model summary is kind of the main one you want to look at. And it basically tells us how much variability diet has in depression. So what this one says, and I usually convert them to percentages because they're easier to understand. So just times it by 100. Who can tell me what percentage of depression diet takes up if you times R squared by 100?
Oh, excuse me.
Bless you. 31%.
Nope.
3.5%.
Good, Diane.
100. Yeah.
By 100. So
Move the decimal point 2 decimal places.
yeah, that's right. So depression takes up about 3.5%. Diet quality takes up 3.5% of depression. So there's about 96% other things influencing depression. This is not looking good for diet, people, in this sample. Okay, adjusted R squared. Now that's our measurement of how well the model fits. So if it's close to the R squared, your model's looking good. So we don't really have to worry. It's quite close. They're nearly the same. R squared change. Now it's the next one. So what it is how much your model has changed from the previous model. Because we're in model one, there was no previous model, so it should be the same as R squared. Yep, so there's a 3.5% change from nothing to model one. And then our significance F change tells us whether or not that change in R squared is significant. So can you tell me, is that change in R squared significant?
Yes.
Yep, good. So when we add social connectedness, what happens? Can you tell me what R squared is if we convert it to a percentage?
50.4.
50%. So when we add social connectedness, it takes up about 50% of the variability in depression. That's huge. That's half.
Mm.
Think about that for a second. Now our R squared change is 46.9%. So adding social connectedness adds 46.9% more variability in depression than just having diet quality. And is that one significant?
Yes.
Good. Our third model, when we add all the other covariates, what is our R squared now?
60 point, no, is it 60.9?
Yep, perfect. So what's our R squared change?
10.5.
Yeah, so adding BMI and physical activity and sleep quality and age only adds an extra 10% on top of that social connectedness. So this is starting to tell a story, a very different story to what we were expecting to find. We're actually starting to see that social connectedness might play a much higher role than any of those other variables, lifestyle factors. Interesting? Not what we came to look for. It was just thrown in there because it was just one of the things that we thought would be interesting to look at. It's now taking over our data set.
You were right that it is interesting to look at.
Yes, it's great though, because it then creates a whole new research question, a whole new line of thinking. Now, Durbin-Watson, this is our assumption, another one of our assumptions tests of independent errors. So we want to make sure that our residuals or our errors are independent of each other. Now, Durbin and Watson, the best way to tell if independent errors has been met, it has to be over 1 but less than 3. So 2 is a really good kind of area for Durbin and Watson to be in. So that's a pretty good one. So another tick, we also now have our assumption of independent errors met. The next box that we look at is our Anova box. Now our Anova box tells us whether our models are significant. Yeah?
Yeah.
Our first box told us what the variability in depression was for each of the models. Anova actually tells us which of the models are significant, but not what variables inside the model are significant. That comes later. But if your ANOVAs are non-significant, then you cannot move forward to interpret the rest of the regression, because that means you wouldn't go on to interpret a non-significant model, right? So this is very important. So all you need to know is your significance levels really in this. So model 1, when we only had diet, is it significant?
Yes.
What about when we add social connectedness in model 2? Still significant. And what about when we add all of our other confounding variables?
Yes.
Still significant. Okay, that's good. So now we can move on to finding out which of those variables are actually significant inside the models. And we would only read model 3 because it's the one with everything in it and it's significant. So this is the coefficients box. We're reading model 3, just this one here. Now, the first thing we want to look at is our T's and our significance of our T. Now, T tells us, our T-test tells us which variables inside the model are significant. So have a look at diet. Is diet significant?
No.
No! What? That's my whole hypothesis.
Oh, shit.
Keeping in mind that this was done in a cross-sectional survey, only at one point in time. So it doesn't tell us about causality. It doesn't tell us cause and effect. And it doesn't also tell us about people's changes in dietary patterns over time. Cool? It's just a correlation. And keeping in mind that the measure that we're using, that dietary quality score, is highly disadvantaging the vegans and the vegetarians, which is the predominant amount of our data set, yeah? So that could be the reason that it's not significant. Let's look at social connectedness. Is it significant?
Yes.
Cool. So because it's significant, we can go on to interpreting it. So if we have a look at our standardized beta, can you see where standardized beta is?
Yeah.
Next to T. What is it for social connectedness?
Minus 0.612.
Yeah. So what that says is that as social connectedness increases by 1 standard deviation, depression will decrease by 0.6 of a standard deviation. So that's quite large. That's quite good. I won't get you too confused with the rest of it. Over here, right at the back end of our coefficients table are our co-linearity statistics. So this is another one for multicollinearity. Remember back up in the correlation matrix, we looked at anything that was like 0.8, 0.9, any variables that were too closely related. Tolerance and VIF also measure this. So if tolerance is less than 0.2 and VIF is greater than 10, then you have a problem. But these all look pretty good to me. They're all 0.9, 0.8, and the VIF is around 1. So we've got no problem with multicollinearity. So it's a double check. So there's another tick for another assumption. Let's look at BMI. Is BMI significant in our third model?
No.
No, it's not. Is age significant?
Yes.
Yes, we're going to have to rerun that though because I had those older people in it. So we'll go and have a look. So our standardized beta tells us that as age increases by 1 standard deviation, depression decreases by 0.089, so not by very much, but it's still significant. Sunlight exposure, is it significant?
No.
No. Sleep quality.
I can't see it, but yes, I think it is. Yeah.
It is. Sleep quality is significant. Another finding we weren't expecting. So what that means is that the standardized beta is negative 0.328. So as sleep quality increases by 1 standard deviation, depression decreases by 0.32 standard deviations. Is physical activity significant? No. So what we're basically finding here is diet's not significant, but social connectedness and sleep quality are. This is the point where you go back to your supervisors and you say, "Hi, help me." No, you don't say that. You just have to write it up that way. In this data set, we found diet quality was not related to depression. Cool. Don't need these 2 boxes. This one here is important. Casewise Diagnostics. Where did you go? Here it is. Okay. So remember when we were talking about residual outliers? So any case that has an outlier on 2 variables, basically, and is skewing your data. And it might be case number 68 doing this, would be my guess. There's a standardized residual of 3 over 3. Anything over 3 is cause for concern and means that it is an outlier in your data set. So you might need to do something about that, like transform the data set. If our residuals are skewed, which we'll have a look at in a second, we might have to apply some form of transformation. So let's have a look at that. So these histograms here are not histograms of normality, like we looked at before. These are histograms of our normality of our residuals. So remember, our residuals are the error that we find in our model. The larger the error, the worse our model is. The smaller the error, the better. So that's looking kind of normal to me. What do you reckon?
Yep.
It does, hey? I still reckon this person here is number 68. And then it would be even more normal without that person. The PP plot's kind of snaky. So that's suggesting that we might have a problem with skewed residuals. And here's our scatter plot. Now the scatter plot tells us two things. One, linearity, like we looked at before, whether we can put a straight line through that data set or whether it's kind of a U shape. And homoscedasticity, which is kind of like homogeneity of variance. Yeah?
Mm.
If the dots are spread out like this in a cloud form, then homoscedasticity is there's no problem with the assumption of homoscedasticity. If they're funneled like this, with heaps of dots up the top and then funneling into a point at the bottom, that means you've got problems with homoscedasticity. So there's another assumption we can tick off. So many assumptions. We've met most of them except for maybe normalized residuals. Maybe. It's not that bad, to be honest. And maybe that one outlier is a bit of a problem. But apart from that, this is all looking pretty good. Okay. So that's depression and standardized residuals. This is depression and dietary screening tool. Still not funneling. Social connectedness. There's a good relationship there, look at that.
Mm.
Whereas up here with the diet, it's like kind of like, remember we couldn't see if it was on the incline? But that one, there's a very dramatic negative incline on that, isn't there? On the social connectedness scatter plot. All the dots are kind of going like this. Cool. BMI kind of doesn't look like there's any significant relationship. It's kind of on a straight line.
Mm.
That's your partial regression plot. For age, same sort of thing. It's significant, but does it really look like it's got any form of... No, not to me.
No.
And sunlight exposure, same thing. Sleep quality should have an incline. Yep. So can you see how that's going like this? All the dots are going that way. And then physical activity also kind of just everywhere, not really any form of a relationship. So that's regression for our population. Any questions? No. Good job. So the final thing we're going to do is we're going to assume that our research question is a little bit different. We are going to look at depression, and we're going to split it by the three groups: vegan, vegetarian, omnivore. So our research question is now changed to, is there a difference in diet quality between vegans, vegetarians, and omnivores and depression? So exactly the same thing. So first, before we do anything, we need to split the groups. So we go to data, split file, compare groups. We want to compare it by diet. Okay. And then we just run exactly the same regression as we ran for dietary screening tool. And we just take out dietary screening tool and we put in the plant-based dietary index. Because remember when we did our ANOVAs last week and we split them by groups, the plant-based dietary index came out significant and the dietary screening tool did not. Cool, but everything else stays the same. Off we go. Okay. Now I'm going to get you to tell me some things this time because I explained them to you last time. It's exactly the same output. So you might be able to help me read and interpret this. So once again, we've got our descriptive statistics for our omnivores, vegetarians, and vegans. So what I want you to tell me is a little bit of a recap from what we looked at last time. What is the mean of depression scores for omnivores?
12.
Yep. What about vegetarians?
19.
And vegans?
15.5.
Which group has the highest depression rates?
Vegetarians.
They do.
How interesting.
Yeah. It
We're
may not
talking
have
about-
anything to do with diet and lifestyle, though.
No. We talked about that last week. Yeah.
Mm. Yes. But it's weird that they're higher than vegans as well for those reasons.
Yes.
But omnivores have the lowest depression scores. Very interesting. Okay, let's have a look at diet quality. What's the mean diet quality for omnivores? So it's plant-based index total. What's their mean for omnivores?
3.6.
Yeah, so this is out of 100, so that's pretty good. What about vegetarians?
72.
And vegans?
77.
Who has the highest diet quality score?
Vegan.
And who has the lowest?
Omnivore.
Omnivores.
Yeah, but that might be because we changed those scores around. However, I think when we looked at the dietary screening tool, the omnivores were still lower, which is interesting. Cool. Oh, let's look at BMI. What's the average BMI for omnivores?
26.
Vegetarians
27.
and vegans.
24.
So who has the
25.
highest?
The vegetarians.
Because if we remember, case 68,
Oh, of course.
with
you'll be
that
buying-
massive BMI was a vegetarian. So she'll be skewing that BMI data massively.
Yes.
Mm.
And there's not, like, that's not a huge difference
No.
between, there's not a big variation. Is that the right term? There's not a
Of
big
BMI,
variation.
which is very interesting, isn't it?
Mm.
Cool. Yeah, they're interesting ones. Okay. So this is our correlation matrix. So if you can tell me with the omnivores, please, to the top row and the top box, what is happening with depression and our diet? Can you see my arrow or not?
Yes.
Oh, that's good. So I can kind of point you to the statistic that I need. So what's happening there? As diet goes up, what happens to depression?
It decreases by 12.7%.
No, that's a good try though. So it does decrease, but this is correlations. This is a relationship. This is not, we can't convert these to percentages yet.
Right.
That's why to convert to a variability, you need to square the correlation, which is y(r) squared.
That's right.
Is
So this is a
variable.
number between -1 and +1.
That's right. So the
So-
closer it is to 1, the stronger the relationship. The closer it is to 0, the weaker the relationship.
So that's not super close.
No. What about social connectedness in omnivores? What do we think? As social connectedness goes up, what happens to depression?
Oh, it goes down even more.
Yep.
That's
So all
26.
these are looking exactly the same as what we saw in the total population. As BMI goes up, depression goes up. As age goes up, depression goes down. As sunlight exposure goes up, depression goes down. So omnivores are showing the same sort of trend as the total population. Have a look at vegetarians, same sort of thing. Yep, exactly the same trend. And vegans, same trend. Everything's negative except for BMI. See you, Dennis. Cool. Then you want to go through and have a look at your multicollinearity of your correlations. Now, if we don't want to do that, if we find it very difficult to read through all of those data points, then we can just look at our VIF and our tolerance later. So we might just do that. Okay, that's how we entered our variables. Diet in model 1, social connectedness model 2, and other variables into model 3. And here's our model summary. So the most important thing in our model summary is our R squared, because it tells us our variability in depression. So for omnivores, can you tell me what the R squared is for model 1 when we add just diet?
That's 1.6%.
Yeah, not really
That's
very
not
much.
very much.
And look at our adjusted R squared. That's saying something. It's supposed to be close to that R squared. The model fit might not be very good on this one. Okay, and is that significant, that R squared change? No. So going from nothing and adding diet doesn't seem to have a significant change. It's a worry. Keeping in mind we're using the plant-based index this time, not the dietary screening tool. So it's another measure of diet quality. Okay, so when we add social connectedness, what happens to our R squared change? Well, to R squared, what happens?
It increases.
Yep, so how much variability does social connectedness have in depression for omnivores?
38%.
Yep. How much does it have for vegetarians?
Oh, 63%.
And vegans?
50%.
Interesting. Cool. So that R squared change, that's significant for omnivores. And then when we add our other confounding variables, how much more does it add to the model?
%20%.
Yep, very good. And here's our measure of independent errors, our assumption. All of those are looking nice and around 2. So that is our independent errors assumption met for all of our diet types. So let's look at vegetarianism. What have we got here? We've got our R squared for diet is 0.02, so that's 2% variability in depression. And that's not significant either. Social connectedness is 63%. It is significant. And the confounding variables add 6%, but that's not significant. So in model 2, only social connectedness is significant for vegetarians. So we couldn't go on and measure like the vegetarians. It seems only social connectedness has a significant R change, which is interesting. But look what's happening with vegans. This is interesting in itself. So in vegans, which is our highest amount of sample size, if you remember, because omnivores and vegetarians have a very small sample size. Vegans have got over 150 participants. And what's happened? So what's our R squared for diet?
5.8%.
Yeah, so nearly 6%. And is that significant?
Yep.
Yeah, because our sample size is bigger. So potentially the findings from the last one we did on our population and on this may just be because we haven't got a significant amount of sample size in each group. What about social connectedness? What's its R squared? 50%, and it's significant. And then what about, what about when we add our other confounding variables?
4%, and it's significant.
So it adds about 14%. Good. So let's go and see if our models are significant. Tell me about this. This is very interesting indeed. So when we have diet only in our model, it's not significant. But then when we add social connectedness and our confounding variables, our model becomes significant. Can you see that? In all of them, in vegetarians and omnivores, that's the case. So model 1, just diet and depression, not significant. But when we add social connectedness and the other confounding variables, that makes the model significant. So what that is saying is that there's no actual significant effect of diet, but when you add other lifestyle factors in, like physical activity and sleep and sunlight exposure and social connectedness, that they then take up and make the model significant. However, in vegans, that's not the case, because diet quality is significant in model 1. So then what we do once we've looked at our ANOVA is we go and have a look at our coefficients in model 3 for all of them and see which ones are significant. So in model 3, diet's not significant. The only things that are significant in model 3 for omnivores is social connectedness and sleep quality. Is this a trend that we're seeing from our last one when we looked at the population data? Was that the same result that we found?
Yep.
So the only things that are coming out is sleep quality and social connectedness for omnivores. When we look at vegetarians, where's the significance? Here it is. In model 3, vegetarians, social connectedness. Oh, sleep quality's dropped out of that one. It's not significant anymore for vegetarians, so just social connectedness. And then for vegans, it's a different story again. So model 3 for vegans is this one. Diet's still not significant. Social connectedness is, and sleep quality. So finding exactly the same thing across the groups when we split them. Not great for my research question. Good for other things though. Okay, don't need those, don't need those. Residuals, here we go. Anything over 3 is bad in our standardized residuals. So omnivores, nothing over 3. Vegetarians, nothing over 3. Vegans, nothing over 3. So there is no real outliers in our residuals. So that's an assumption that's ticked in this one, which is interesting because when we did the population data, there was one residual outlier, which has kind of disappeared when we've broken it down into groups. That's interesting as well. Here's our histogram, our normality of residuals. What do you think that says?
Pretty normal.
Yep. Yeah, it's looking okay to me. PP plots are a bit snaky, snaking around that line. Yeah, they're not looking great. Scatter plots, they're not really funneling. Not too bad. Obviously, these are showing that sleep quality and social connectedness are the only ones that really have any sort of like incline or angle. There's social connectedness, obviously, with its negative incline. Everything else is kind of like straight across. Very interesting indeed. Same sort of thing. Good job, everybody. Gonna have to run all those data again with those age points taken out. That was interesting. I thought we got rid of those last week. That was weird. Anyway.
Megan, did you just save that then, all of that data? I didn't notice whether you saved it. I was just having a question actually about the saving. Do you need to save kind of both views, so your data and then your variable and then everything as you go along, and save it as something different?
You can. What I normally do is I play around with the data like we've done today, and I look at things and see what's going on, and I wait to save my output until I do my final analysis. because you will change things and you will like remove people and you will like as you're going along, and then right at the end I just redo everything for the final time and then save those outputs as the final ones to put into tables and things.
So you do save your data in a separate file as like all of your analyses though?
Yeah.
Yeah. Okay.
Definitely do. And I save the data as different things as I go along. So I save it after I clean the data. I save the raw data set so that you always have that raw data so that if you make a massive mistake one day, you can go back and start from the beginning. And then that's okay. Then I save at the data cleaning stage after I've cleaned all the data and put everything in, it's nice and clean. Then I'll save after at several different stages if I remove people, because once you remove people who are outliers or assumptions are going wrong, or you found people who are over the age like we did before, you just have to save it again, because if that's a mistake, then you don't want to have to go all the way back to your raw data and start again. So saving at stages is super important. Cool. So that was regression. Any questions about regression?
I have a question, and I might have the wrong end of the stick, so feel free to tell me I've got it all wrong. But I'm trying to work. I understand quite a lot of what you're saying, thank goodness, but some bits of it just are beyond me.
Yeah.
You've just done regression, and you've done it sort of those 3 steps or those 3 different blocks. I don't remember what the term was. Is there a big difference between that and an ANCOVA?
Yeah, so Anova.
Okay. Yep.
Any regression is always on when you have a continuous DV or a continuous data that can lie on a continuum. Anovas are done when you're looking at categorical data between groups. So you could run an ANCOVA on the exact same data and see what happens. So there's more than one way to do a data analysis.
Yeah, that's what I heard you say that, and I went, oh, I've read that before. And then just the way you put it all together, I'm going, that looks really similar to ANCOVA with my limited knowledge.
Yeah.
Okay,
Yes.
Okay, that's all I need at the moment. Anything else will probably confuse me, but thank you.
Yeah, so that is one interesting thing, that there is more than one way to analyze data. And in my honours year, I ran regressions on my depression data and as a continuous variable, and then I decided to dichotomize my depression variables. So that means I found out in the CESD that depression has a cutoff score. So anyone who has depressive symptoms was anyone over 16, and anyone who scored less than 16 was not depressed. So I took that depression score and I dichotomized it into depressed and not depressed. And then it became a categorical variable. And then I ran what's called a logistic regression on them, which is very similar to what we've just done, but running regression on a dichotomized dependent variable. And the funny thing about it was that the results came out the same because they were very, very similar. And it was the same sort of variable. So you can do things different ways depending on what your research question states.
How do you get the uncertainty of your model?
The certainty of the model?
The uncertainty, yeah.
What do you mean, the uncertainty of the model?
Like how correct it is, or?
Yep. So using all your assumptions testing will help you with that.
Mm-hmm.
Yep. So all those assumptions that we talked about today, making sure that they're met, will give you greater certainty in your model.
Okay.
If you miss one of them, like we have a little bit of a problem with an outlier in one of them, then you would talk about either transforming your data or bootstrapping or doing something similar.
Mm-hmm.
Now we need to talk about what you would like to do next week. So next week is our final week, and I would like to do show you an analysis that you are interested in having a look at. So what is everyone kind of wanting to do from here or learn from here?
I'm keen to know how you work out what to do, like you said, suggested transforming or bootstrapping, what to do with data when it doesn't meet the relevant assumptions. And I realize there are lots of tests and so lots of assumptions, but
Yeah.
in my case, I've got two different things going on. And as far as I can tell, both data sets do not meet the relevant assumptions, and I can't work out where to go. So it'd be nice to have some idea of how to work out what to do next.
Yes, good, excellent. We can do that. We can do transformations and bootstrapping and things next week. My question at this stage, if you have run things and your assumptions are all coming out not met, it is a very important thing to sit down with your supervisors, tell them that that has happened, and ask them what they would do in this situation. Just because if you don't sit down and have that conversation and you go and do your own transformations, they may not agree with the ones that you chose, because there are different transformations that you can do on the same data. So recently I've done a square root transformation on my data set, and then I went and showed my supervisors, and they're like, it might be better if we actually dichotomized the depression variable and we did a logistic regression instead, similar to what happened to me in my honours year, rather than doing a transformation. So supervisors will always have their ideas of what they would like, and it's best to listen to them and follow their lead when it comes to that sort of thing.
Are we doing factor analysis next week?
We can. Would you like to do some factor analysis next week, Gurmeet?
Yeah, it would be good.
Okay, so factor analysis, for those of you who don't know what factor analysis is a tool that we use. Say we create a survey and we write all the questions for our survey, but it's not pre-validated. So it's not a survey that someone has already done, like we were talking about at the beginning of the tutorial today. It's not a scale that someone has already done and made sure that the questions align with each other and are actually measuring the construct that you're trying to measure. So if you create your own survey and you have all your survey questions, you then need to validate that survey and make sure that the questions that you're asking are actually measuring what you want them to measure. And doing a factor analysis can decide that. So we can look at that next week.
Can I ask you a question? Doesn't
Yes.
the KMO tell you whether it's good enough? Like I know that mine came out with, I think, 0.8 or 0.9 for that, which is telling you that it's suitable to factorise. Is that right?
Yep. So we'll look at that next week. We'll have a look at KMOs, eigenvalues, all the things that tell you whether or not the questions in your survey are actually answering the construct you're trying to measure.